Welcome back to Nanoflo, from Blink to Bots. In this series, we're learning how to control real-world hardware using Nanoflo and Arduino, with flowchart logic instead of complex code. Let's jump in. In today's episode, we're going to take a look at how we can incorporate an input to control that LED, and go a step further, looking at PWM as an output for my PWM LED on my Freenove board, using a potentiometer to control the variable output that will change the brightness of my LED. So this is where we left off last episode, with our blink outputting our 13 onboard LED to off, delaying for a second, turning it on again, and delaying for one more second. We want to take this a step further by adding in an input to begin my code. And this is a really handy tool for initializing your code. Say you're doing a sumo bot project, which we'll look at later on, where you would like your students to place the bot down on the table, press the button to start the program. On my Freenove board, my inputs are input pull-ups by default, and therefore in my settings panel here, I can change my type to an input pull-up rather than an input. If you had a normally tied down input button, or that's how you've set up your switch or button, then you could just use the normal input setting. So I've set mine to an input pull-up, and you can see here, when I press my blue button, I can see that turning on and off as I press and let go. Tying that into my blink circuit is actually quite simple. First, I'll shift my blink start node up so that I can fit in a decision node. And a decision node is what we use to interact with any inputs, both analog and digital. So under the flowchart tab, I'll take a decision, and I'm just going to slot that right in underneath my start node here. I'm looking for input 2, which is my button, and I'll be checking whether that input is on or off. Now it's currently on, so I'm going to wait until that input is turned off. If the button hasn't been turned off, I'm going to loop back to the top of my code and keep checking to see if that button has changed or the state of the button has changed. If it has changed, then we can move on to starting our code. And in this case, we want to continue into blink. So we'll just test that works by hitting play on our emulator. You can see that my LED is left on from the last state it was in. When I press my button, I'll move through to the flashing mode in my LED. Now, good practice in code is actually to initialize that code. So we want the state of our LED to be off from the get-go, and that would have prevented this issue where my LED started in an on state. So I always teach my students that the very first thing they should do in their code is to initialize that code with whatever their outputs might be. So in this case, we want to actually start with pin 13 off. So this time when we press play, you'll see that my LED will turn off, and then we'll be sitting or waiting for is input 2 off. It's currently in a high state. We're waiting for that low state to occur. Once it does, we can cycle through. We could continue a step further with that and press the button again by removing this section of our code to turn the LED out of the flash state and back into our off state or our low state. So I put another decision in and say, is the button off again? Once we're checking, we can continue to flash until my button has been pressed again. And once it presses again, I can turn it off and wait for that button to be pressed one more time. Now, if I leave it like this, there will be no delay or no time for me to release the button for the LED to be checked again. And so we should have one more small delay just below this to allow for my finger to release the button. Let's say 50 milliseconds. That will happen before my decision is pressed. So we now go back into our emulator, we press play. We're going to wait for the button to be pressed. Once it is pressed, we're in a flash state. And every time it works through that state, it's checking to see if the button's been pressed right at the bottom of our code here. If I press the button again, my button has been pressed. We're waiting for it to be pressed again to enter back into that state. Really handy for a marble machine exercise or an automated machine exercise where a marble arrives onto a micro switch and you're waiting for that marble to pass through or that item to pass through, and you need the micro switch to be pressed and released to start the motor again. Now, previously I mentioned my onboard PWM LED, which is attached to pin 6. So once again, when you hit our drop-down setting menu here, you can see we have a range of different settings or pin types that you can set that pin to. And so we're going to look for PWM here as our output. And whilst we are connected, I should be able to go through the process of sliding that bar up and down. And very subtly, you'll see an increase in the light. So it's dimming from low value to high value. So what can we do with that value? Well, let's play with an analog input rather than a digital input. I also have a set of potentiometers on my board here, which as I adjust these potentiometers, you can see them adjusting on my emulator. This is another great demonstration of how Nanoflo can help you with initializing code, because you can live see your input data from your Arduino whilst you're using it. Very handy for light-dependent resistors, for ultrasonic sensors, to be able to see those values live. So how can we utilize the analog to manipulate our PWM value? Well, we can actually map that with a let. So we're going to run a simultaneous code here where we have our PWM LED. We're going to build a flowchart now that allows us to output our LED brightness by mapping it to our analog input. So PWMs run from 0 to a range of 255, whereas the analog input runs from a range of 0 to 1023. So the first thing we need to do is actually map a variable that allows us to use that value, or that range, from 0 to 1023 as 0 to 255. So the first thing we'll do is start by dropping a let in and adding a variable, our variable A. We're going to set that variable to our analog input, which is analog 1, and then we will divide that number, whatever it may be, by 4.01. Just to check that this is all functioning, I'm going to put that into a loop and open up my emulator tab with my variables table and just emulate that value. What I should see is at the very top of that value, 1023 analog value, I'm receiving a map value of approximately 255. And as I scroll down to 0 in my analog input, you can see that value changing and mapping to 0 in my variable. So I've now mapped the value very simply from our analog to our PWM value. Once again, a very handy way to be able to describe to students what the C++ map is doing in Arduino code, and give them a very realistic mathematical understanding of why these values must relate to each other and why you must map those values. So now that we know that that is working and functioning as expected with the values that we're expecting to receive, we are going to map our PWM as an output now, just with a simple output node, by setting our PWM to that new variable that we have. So rather than giving it a value to move to, we're going to move it dynamically with our variable. All we need to do now is check the value in a loop, and we should be able to manipulate our PWM output through our analog input. So back in the emulator tab, we will select play, and we should be able to see our brightness at full. And as we adjust the brightness of our LED with our potentiometer value, we will see that change. So both in the emulator tab and on the onboard Freenove LED, we can see that value changing. Now, another unique feature of Nanoflo is we can see in our code that the blink is waiting for our input state to change. And so we have this feature where Nanoflo allows you to run simultaneous codes, simultaneous inverted commas, as there is a state machine built into the back of Nanoflo. So in C++, where you would have to teach your students how to run a Miller's function, where they have a state machine checking the timings so that you can run simultaneous, once again, inverted commas, code, Nanoflo allows you to do that simply by running separate start nodes. And so I can manipulate my LED as I was before, whilst waiting to press the button, and once again, we have that flash occurring exactly at the same time. And so we have this simultaneous code function, which once again is a very unique feature that Nanoflo allows for. So it was a very quick demonstration of an input manipulation where we have both digital and analog, manipulating our outputs of both PWM and LEDs. As we move forward, we'll look at inputs such as ultrasonic sensors or LDRs, light-dependent resistors, that we can use to create much bigger projects like solar trackers or robots that are obstacle avoidance. Don't forget to like and subscribe and leave a comment if you're following along in your classroom or makerspace.